Looking again at some of our data, this is just the beginning of the data set. It goes on up through about 13 washers, I believe. But this is data for a trout coasting 49 centimeters from rest. 5, 6, 7 washers, delta T as we saw before, 1.98, 1.71, 1.58 seconds. And we want to infer the acceleration in centimeters per second squared. The accelerations we get are shown here. And how did we get those accelerations? Well, remember that we just saw that, I don't know what that delta T equals is doing there. Let's go ahead and just kind of scratch that out. But we saw that the acceleration was 2 delta S over delta T squared minus 2 V naught over delta T, the equation we just solved. Delta S is just our 49 centimeters, so 2 delta S is going to be 98 centimeters, and that'll be over delta T squared. From rest means that initial velocity is 0, so this term is 0. We don't even have to write it down. This is going to be our acceleration. So we went through a little bit of pain to solve an equation for A, but now we've got a formula and we can just punch in 98 over the square of 1.98, and we know that that's going to give us our acceleration in centimeters per second squared. It's going to be 24.9 centimeters per second squared, and so forth. So we very quickly get our accelerations, which we can then plot. Now, in class, we used derive. We actually used derive with the data set to do the calculations for acceleration. We got a best fit line. Acceleration is 6.8 F minus 6.5, where F stands for the number of washers. This means that to get the acceleration in centimeters per second squared, we multiply the force in number of washers. Whatever force gravity exerts in a washer is what our force is going to be. Multiply that by 6.8 and then subtract 6.5. If you were doing this without using derive, you would plot a careful graph. You would draw your best fit straight line. You'd take 2 points on that line, not 2 data points, but 2 points on your best fit line, and you'd calculate the slope. And that would go here. The slope is 6.8. The minus 6.5 is the y-intercept, or in this case the a-intercept. Just using what we know about the equation of a straight line, we very easily determine what the line would be once we've graphed it and graphed our best line. So the conclusion we draw here is that for the system that we observed, the acceleration is 6.8 centimeters per second squared times the number of washers minus 6.5 centimeters per second squared. This says for every additional washer we're going to have an additional 6.8 centimeters per second squared of acceleration, because every time we increase this number by 1, the acceleration is going to increase by 6.8. And that 6.8 is, of course, the slope of this graph. It's 6.8 centimeters per second squared per washer.